This is exam 2 for the fall 2019 semester for MA166. So we have, this is problem 1. We would just have this limit as we're taking n goes to infinity of some stuff inside of square roots and cube roots. So the first step here is to realize that as n grows bigger and bigger, if we look at just the terms inside of the square roots, only the highest power n terms will survive, essentially. So if you're thinking about plugging in 1,000,000 in here for n, which can kind of be our approximation of infinity, we'll have 1,000,000 squared times 3, and then we just add 1. And that's not going to be a lot in comparison to this 1,000,000. And same thing down here. We have 1,000,000 cubed, and we're only taking about 2,000,000 from that. And so as we get bigger and bigger, it becomes more and more true that this ratio is equal to just this expression. Okay, now we can just mess with the square roots and cancel our powers and square roots out. So we'll say that this is equal to the limit. At the top, I'm going to break the square root, so I'm going to make it root 3 times the square root of n squared. I'm going to say it's the square root of n squared. And then on the bottom, I just have the cube root of n cubed. But the numerator and denominator here are nothing but n. So this is n over n, which we can cancel out. And that just leaves us with root 3. And that would be answer choice E. Okay, so now we're on to problem 2. We have this rational function, and they want us to write it in partial fraction decomposition form. So the first thing to do is to look at the denominator and make sure that it's either a product of its factors or factor it to make it a product of the minimum factors. So this x minus 1 squared term we can't break down anymore because it's just a binomial. But we're looking at this other quadratic here and we're saying, okay, maybe we can just factor it. So the easiest way that I want to look at, if I don't immediately see a way that I can factor this, I like to look at the roots of the polynomial with the quadratic formula. So that's what we're going to do. We're going to say the roots are going to be negative b plus or minus the square root of b squared minus 4 times a times c over 2. And we see that in the radical here, we have negative 4. And that means that this is a complex number. So that's all that this means here. So this belongs to the complex numbers, which means that we aren't going to be able to factor this anymore in our world of real calculus. So we're stuck to the real numbers. So that means that we don't want to factor this thing any more than we have it written as here. So now with that figured out, we just need to follow our partial fraction decomposition rules. So I'm going to look at this root first, and I'm just going to go left to right. For this root, it's unfactorable, and it's a power of 2. So in my numerator, I need to put a power of 1 polynomial, and just put that over what we have there. And now I look at my other root, and I see it's x minus 1 squared, so I have 2 of these, which means that I need to have 2 terms that correspond to this root here. And since it's just a binomial in the squared, I just put a constant. So that's my first term. And then my second term is this. So I'm building up here. That's what we call building up the roots. And that is my answer, and that would be answer choice A. Okay, moving on to problem 3. We're given this integral, and we're asked what substitution should we use to solve this integral. So just looking at this immediately, the options are a bunch of trig subs. But looking at this immediately, it's not clear how even a trig sub would help in the first place. So we want to get this integral in a form where we can automatically recognize I know what trig sub to use here. Okay? And we know that usually looks something like, if we have a square root in here, this usually looks something like something squared plus 1, or minus 1 or 1 minus something squared. So we want to get it in one of those forms. So something like this. Because we know here we can just make this equal to tangent. This can be cosine or sine, etc. So let's look in here, and we have a quadratic. And so one tool, if you puzzle about it long enough, that you could come up with as a great idea to maybe mess with and play with, is completing the square, because we get something squared plus some constant. And so maybe we can finagle things to make it so that we get to our desired form. Okay, so we want these forms, right? We want something like this. Okay, and that means we want to complete the square. So to complete the square, I'm going to look at my x term, and I'm going to do b over 2, and I'm going to square that. And so that's going to give me, I have 3 here, so that's 3 halves is my b over 2, which means I'm going to get 9 over 4. So now I'm going to go inside of my square root, and I'm going to do 3, and then add, or I guess, we'll add 9 over 4, and then we'll subtract 9 over 4, and we'll leave the rest. So you can see that this is just 0, so I haven't changed. So this and this are equivalent. But now I can group this term, and this term, and complete my square. And I can just group this term and this term together to have my constant. So what that looks like is that I get the square root of, if we do 3 minus 9 over 4, that's 12 over 4 minus 9 over 4. That gives us 3/4. So we have 3/4 plus x plus whatever our b over 2 was. So that was 3 halves. Okay, fantastic. Now, hey, look. We kind of have something that looks like, I guess not this one, but we have something that looks like this one. So, our goal is essentially to, well, I guess first I should ask, what substitution would we make? And let's say this, right? Because 1 plus tangent squared is secant squared, and then we can get rid of the square root, and then we just have to integrate secant. So, let's say, right, now we want this term. We essentially want this term to end up being tangent squared. So what we're saying is we want tangent, let's call it a theta, equal to x plus 3 halves. Okay, but we got to be really careful here, because if we just have that, then we get the square root of 3 over 4 plus tangent squared, and that's not going to work out for us. We want this to be a 3 over 4 tangent squared. And so the constant that will get us that is having a root 3 over 2 in the front of this tangent theta. Now, we just have to solve for tangent by multiplying by a 2 and dividing by a square root of 3. We get 2x over root 3 plus 3 over root 3. And our answer choices aren't exactly in this form. In particular, this constant's off. So I'm going to say, what if I try to just normalize it? I'm going to put my radical in the numerator. So the first term will stay the same. And then I'm going to get 3 over 3 times root 3. And that's perfect, because this is one of our answer choices. And that answer choice is, let's see, B. That answer choice is B. That's the square root of B. So we are given this sort of setup. So there's a bathtub, and its wall looks like a parabola, y equals x squared on one side, and it's filled up to 1 meter with water. And the question wants us to find the total amount of force being applied to this wall, given that the pressure is equal to 10 to the 4 U newtons per meter, where U is the depth. So if I'm at 1 meter depth, if I'm all the way at the bottom of the tub, I'm going to have 10 to the 4 Newton per meter, squared. Okay, great. So the key relationship to remember with these problems that involve water and stuff, and I want you to relate it to a force, is that force equals pressure times area. Now, right, the pressure depends on our y value, and therefore our area will also change as we move up on our y. So the pressure is going to be constant at our y level, and our area will be changing, and so will our pressure as we go up. So what we want to do in that case is take the approach where F equals the integral of a bunch of little forces, dF. So now if we go to the differential form of this, we're going to do, we have a bunch of little dFs, pressure times our little areas. So if I draw the diagram back over here, if we look at a particular y value, let's look at here, I can draw out a rectangle where the pressure is constant, approximately constant along this whole rectangle, and is truer and truer as I get smaller and smaller. And you can see that half the length of this rectangle is x, and the height is this little change in y dy. So that means our little area is going to be 2x dy. We know we're going to be integrating this, so with an eye towards the future, we're going to make the relationship where we have y equals x squared, so we know that x equals square root of y. So then therefore our little area will be 2 root y dy. So now we have an expression for our little area. Now we just need an expression for our pressure. And they give it to us, but we need to relate this u to y. So if I'm at y equals 1, or if I'm at y equals half a meter, for example, my depth is half a meter. If I'm up here at maybe 0.75 meters, my depth is only 0.25 meters. So if I'm at y, my depth is this distance, and my y is this distance. And so what that tells me is that my u is equal to 1 minus y. So therefore my pressure is 10 to the 4, 1 minus y. So now we can just plug all this information into the integral. So we have our little df in our integral, and that involves our pressure. So we have 10 to the 4, 1 minus y, times our little area, 2 root y dy. And our y goes from all the way from the bottom of the tub to the top. So from 0 to 1. Now, all that's left is to integrate. So we'll take a 2 and 10 to the 4 out of the integral. And we'll distribute this root y into this 1 minus y term. So we have y to the 1/2 minus y to the 3/2 dy. And now we're just going to simply do the antiderivative of that. We're going from 0 to 1. This term is 0 when you plug in y equals 0. So all we're left with is 2 times 10 to the 4th, 2/3 minus 2/5. That's going to be equal to 2 times 10 to the 4. 10 over 15 minus 6 over 15, which will be equal to 2 times 10 to the 4. 4 over 15. Now, that leaves us with 80,000 over 15. None of our answers look like that, so we try to see, can I take out a common term between these two? And I can. That's a factor of 5, which if I do the math here, let's see, if we take 5 out of 8, this one, 16,000. So we get 16,000 over 3, which is answer choice A. So to recap, because these physics problems are important to understand, I had this situation. The first thing I did was draw this diagram. And I understood that they gave me a function for pressure. I understood that I needed to find the force, so I wanted to relate the force to what they gave me, which is the pressure. And I realized that the force is going to be changing as my y changes. So I needed to think about the little forces at each y value and add them up. So I needed to find dA, and that's done with this diagram. And then P, I just related depth to y, and then I just carried out my integration. All right, so problem 5, we're moving on to this sine and cosine integral. The goal with every one of these integrals is when you have two of these trig functions, the goal is to relate them by the derivative, and then to get everything in terms of one of them, and then leave one of the other ones behind to do your u substitution. So what I mean by that is, for example, right, I have sine cubed and cosine to the 4th. So I know that the derivative of cosine is equal to negative sine. And so I know that I can use this to my advantage with u sub. So I'm going to go ahead and I'm going to take out just one sine term, and I'm going to bring it over and group it with the dz. You know, as you're solving this integral for the first time, you might play around with some options, but the common pattern to see is that the one with the even power is usually the one you're going to try to get everything in terms of, because the one with the odd power, you can take one out, and then we're going to use the Pythagorean identity to make everything in terms of just cosine. So, right, I gave away my hand. We know that we want to change sine into cosine, and we can do that with the Pythagorean identity. And so that makes sine squared 1 minus cosine squared. Now we're going to leave cosine, and we're going to have this sine out here. And then we'll use u sub to say u is cosine, because that's what we tried to get everything in terms of. We know du is negative sine dc. And look, we have sine of z dz, so this is negative du here. So I'll just go ahead and bring the negative sign out the front, make everything in terms of u. Now we just have a very simple integral that we need to evaluate. So let's just go ahead and do that. Oh, and got to be careful about the bounds, right? When I go into u land, the bounds change. So let's just do that. Let's just do everything in terms of u. So my bottom bound in z is 0. So if I look at my u and I plug in z for 0, I get 1. So I know my bottom bound is going to be 1. And if I do the same thing with pi halves, plug that into my cosine of z, I see that I get 0 for u. So that means I go from 1 to 0 there. What's usually I find to be helpful is whenever I have a minus sign and some weird funky bounds, I just absorb the minus sign into the integral, because switching the bounds makes the integral negative of what it would be otherwise. So now we have this integral here, and we're just going to do 1 over 5 u to the 5 minus 1 over 7 u to the 7. That goes from 0 to 1. Evaluated at 0, this expression is 0, so we know we just have to do 1 over 5 minus 1 over 7. Plug in 1 for u, and we're done there. That's going to make us 7 over 35 minus 5 over 35, which will make us 2 over 35, which is answer choice C. Okie dokie. So now we're moving on to problem 6, and we want to know the value of this integral. So we're going from 0 to infinity, and we're integrating sine. So the first thing I want to do is actually just carry out the integral. So I know I'm going to get cosine of u, negative cosine of u, going from 0 to infinity. And really, the kicker here is this bound, right? So I want to ask myself, what's the limit as u goes to infinity of cosine? And you know what? I'm going to take you on a graphical adventure on Desmos for this. Okay, so if we go to Desmos here, right, we have a function cosine of x. So I want to compare a function like cosine to a function of that's like, let's say, e to the minus x. Okay. And I want to know about each of them as they go to positive infinity. And you can see a really stark difference here, right? E to the x really slowly approaches 0 and never, never, ever goes away from it, right? So if we zoom out really far and we zoom in really close here, right, we're basically guaranteed that we're basically going to be getting 0 all along this path on e to the minus x. But for cosine of x, we keep swinging between the same values, right? We keep going from +1 to -1, +1 to -1, never really settling at a value. This tells us that cosine, actually, the limit as cosine goes to infinity doesn't exist. So the limit diverges, essentially. And so that's actually going to be one of our answers. So if we go back here, we're just going to say dne, and that is answer choice E. Okay. So this is problem 7, and we want to find this integral, and they give us, on the test, they give us a cheeky little hint, quote unquote, that we should do this with partial fractions. They say it's among the quickest. So let's think about how we can do this with partial fractions, because that's already in our minds, and we want to get through this test quick. So we're looking at this, and we're saying, okay, I know partial fractions, I've got to have a bunch of factors in my denominator. But if we look at our denominator, we recognize this polynomial. This came up earlier in the test. We realized that the roots of this polynomial didn't belong to the real numbers. They were in the complex numbers, which means we couldn't factor this polynomial. So, how do we use partial fractions if our denominator isn't something that we can factor? Well, this requires a little bit of a deeper understanding of the method of partial fractions. Really, where partial fractions comes from is an extension of the idea of when you add two fractions together. It's basically going backwards. So, like, let's say I want to do 3 over 5 plus 1 over 7. What I do is I multiply this numerator over here, by this denominator, and vice versa, so that I can get a common denominator. And then I put them over the same denominator. So partial fractions wants to do what we just did in reverse. And instead of with just numbers, they want to do it with functions. So if we think about this, right? Let's say, if I just had this polynomial in a regular partial fractions problem, I might say this would be my guess for the root. But notice a key issue here. This has something in terms of x squared. And this only has something in terms of x in the numerator. And that is an issue. So let's think. Is there any way maybe I can use this process to get an x squared on my numerator after I go through the process? Because then once I draw that connection to get to something that might look like this, I'm home free. The solution, right, is that I have an x squared down here. If I add just a 1, that's 1 over 1, right? And I just multiply this numerator by this, and I end up with an x squared plus other stuff in my numerator. And boom, I have an x squared term with my desired denominator. So that's actually going to end up being how we solve this problem. So we're going to make this our guess, essentially, and we're saying that's equal to x squared over x squared plus 2x plus 2. We want to solve for a and b, so we're going to multiply both sides by this quadratic down here. We're going to get ax plus b plus x squared plus 2x plus 2 equals x squared. You can see that on both sides our x squareds are canceled. So grouping terms by their power of x, we get this. And so we can see this term, in order for this equality to hold, this term has to equal 0 and this term has to equal 0 for all x. And we can see a really easy way to do that. If a is equal to b is equal to -2, we have 0 on both sides. So that's our solution for a and b. So let's go ahead and plug this with our values for a and b into the integral. So we're going to have -2x minus 2 over x squared plus 2x plus 2 plus 1 dx. I'm going to split this up into two integrals, and I'm going to take a 2 out the front of the first term. This integral just evaluates the 2. This integral, we'll have to use u substitution. And the way that I see that is that I have a polynomial of degree 2 here. I have a polynomial of degree 1 up here. So if I take the derivative of this down here, I'm probably going to get something that's up here. And u sub likes the sound of that. So u is going to be x squared plus 2x plus 2, meaning du is going to be 2x plus 2 dx. Now I'm just going to plug that into this integral. So I have minus 2, the integral from 0 to 2. And I'm going to get x plus 1 over u times du over 2x plus 2. This simplifies to being able to bring a constant of 2 out the front in the denominator. 1 over u du. This is just a -1 out here. So essentially, right, and don't forget this plus 2. We're still carrying around this plus 2 from this integral. We have negative natural log of u from 0 to 2. Whoops, right, forgot to change my bounds. Common mistake. And I know that's an issue because I can't plug in 0 into the natural log. So I'll plug in 0 up here and I get 2. And I'll plug in 2 up here and I end up getting 10. So I know I'm going from 2 to 10. I'm getting 2. That's equal to the negative natural log of 10 plus the natural log of 2 plus 2. Now our answer choices don't really look like this. And it's a little bit puzzling if we're not super intimate with log rules. So the way that we solve this, and to get it in the form that they put it on the exam, is that, let me make it a little bit clearer by taking the natural log stuff and making a minus sign out the front of it. We know that the natural log of a minus the natural log of b is equal to the natural log of a over b. And so we'll just do that this is equal to negative natural log of 10 over 2, which is equal to the natural log of 5. And that is an answer choice. And that would be answer choice, let's see, C. Okay, so we have this integral. And as I look at this integral, I try to think, can I do u substitution? Maybe I'll try something out, but you'll find that it doesn't work. And so you're struggling and you're wondering, and you think, well, if I can't do u sub, then it has to be integration by parts. And that is precisely what we're going to be doing here. So, first things first, we need to pick what our u is going to be. Let's think this through a little bit. If we chose the natural log to be dv, we'd have to integrate the natural log. and I don't like the sound of that. So I'm going to choose my u to be natural log of x over 3, so that my du will be 1 over x over 3, and then with chain rule I have to multiply by 1 over 3. So that makes it 1 over x dx. Now my dv is going to be the x squared term. I'll just get this. So now I'm going to go ahead and say that that is u times v minus, and we need to go from 1 to 3 here, minus v du. And of course, let's start by evaluating over here. So if we plug in 3, if we look inside the natural log, we get natural log of 3 over 3. That is going to be 0, because the natural log of 1 is 0. So all we're left with out the front is negative. We'll plug in x equals 1, 1/3 natural log of a third. Now we're going to go minus the integral from 1 to 3, 1 over 3x squared dx. Now we can just take that integral on the right hand side. So it's going to be 1 over 9, not 6, x cubed from 1 to 3. And we'll just work on solving that out. So that is going to be 27 minus 1. Minus 26 over 9. But this isn't any of our answer choices yet, so we're going to look and look and look, and we'll come up with the fact that we need to do a natural log thing. This is the guy that is different. And so what we're going to have to notice is that natural log of 1 over a number is equal to the negative natural log of that number, because the natural log of some number to any power is just that power times the natural log of just that base. So that's 1/3 natural log of 3 minus 26 over 9 is our answer, and that would be answer choice A. So now for problem 9, they're giving us this limit and they want us to evaluate it. I look at this and I instantly think about the definition of E from the perspective of a limit. So we know that the form of E, the definition of E, or the way that it was first discovered, is that if we have this, this is equal to E. So we need to pick a T so that we can get something of this form. And the thing that I always look at, and I always suggest you to look at, is the denominator term here. So if I look at the denominator, I know I'm going to have to pick t equals 4n. And if I take n to go to infinity with the selection here, t also goes to infinity. So I'm going to get my limit in terms of t now. 1 plus 1 over t. But now I have 2n up here, which is equal to t over 2. So by the fact that doing double exponentials gives me a multiplication of exponentials, I can split that outer bit here like this. So that tells me that I have e to the 1/2, which is the square root of e, which is going to be answer choice D. So this is probably the hardest question on this exam. It's hard to get it not really after you've seen the solution, but before you've seen the solution. So I would recommend that you pause the video and see if you can explore the different tools and ways of combining them to try and get the result here. I don't want to spoil it without you trying it first. So please take a minute to pause the video and see, maybe I'll start with U sub. Is there something with U sub that could lead to a promising result? Maybe not necessarily that'll get me right to the result, but that I can use other tools to get me to where I want to go. Okay, so I'm going to assume that you paused and you tried, and now we're going to solve it. So the first thing I'm going to do is I'm going to use u sub, but with an I to the future, I'm going to call my variable t instead of u. So I'm going to set my t. The most interesting thing in this integral is what's inside of that sign. So I'm going to do that, and that means my dt is going to give me this. So let's rewrite the integral in terms of that. If I plug in 0 for my for y, I get 0 for my t. And if I plug in pi for my y, I get pi halves out for my t. It's going to be sine of t. Now, dy, right, is going to equal 4 root y dt. So that's just what I'm going to sub in here. But notice that our t is equal to square root of y over 2. So if I solve for my square root of y, I'll get that it's equal to 2t. So I can just substitute that in for where I see my square root of y. And then let me take the constant out and rewrite it in a way that's more familiar. Boom. Okay. Now isolate yourself from the rest of the problem. When you've just got this integral, what method should you use? Your answer should be integration by parts, because if we pick our u to be t, it'll go away. And this is why I wanted to use t instead of u. So our u is going to be t, our du will be dt, our dv will be sine dt, and our v will be negative cosine. So from there, we really just have basic integration by parts problem. So that's v du. I brought a plus sign out because it's a negative cosine for v, and du 0 to pi halves. If we look at the first term here, plug in pi halves for cosine, that gives us 0. Plug in 0 for t, and that gives us 0. So this term is just 0. Now, we'll have 8 from 0 to pi halves. Cosine of t dt is going to be equal to 8 sine of t from 0 to pi halves. Plug in pi halves into sine, that's 1. Plug in 0 into sine, that's 0. 1 minus 0 is 1, which means our answer is 8, which is answer choice E. So that's the hardest one. This is one of those rare integrals where you do u sub first and then do integration by parts. So understanding how to do integrals like these, reviewing ones that you've seen in class, that will give you a strong advantage in any upcoming tests, because this is one of those more creative, harder to solve type problems. So this problem asks us about this integral, and they want to know if this integral converges or diverges with comparison to another function. And so really, the only way to be super quick in these problems is to just either get lucky or be able to see the entire process in your mind before you even write it out on paper. So I'm just going to bring you through the one correct branch, but likely when you're doing the problem, you're going to try out a bunch of different options that are given to you. So in that spirit, I'm going to say, okay, what if I just chose 1 over t? I want to compare this function to 1 over t and see what happens. Okay, so when I look at e to the minus t plus 1 over t, I can see that in my numerator, right? I have e to the minus t, and I'm going from 1 to infinity. So I know that e to the minus t is always going to be a positive number for any t, even if it's outside of these bounds. So I know I'm going to have a number bigger than 0 plus 1 over t. That's going to be bigger than a number that's just 1 over t. So if this is true for all the t in our range, we also have that this is true. So what we hope is that this integral diverges. Because if it converges, we can't say anything about this integral. Because we would just have a number is less than that integral. So either it could converge or it could blow up to infinity, because there are numbers that are bigger than whatever this number could converge to. And also infinity is bigger than it. So let's just take a look at this integral. We got the integral from 1 to infinity of 1 over t dt. That is going to be the natural log of t from 1 to infinity. The natural log of t, as t goes to infinity, is actually infinite. The natural log keeps growing. And you can think of that as the natural log of t gives you the exponent that you have to raise e to get that number. So if I keep increasing the number, I have to keep getting higher and higher exponents of e to get the number out. So it makes sense that this should blow up to infinity. So that means that I have infinity is less than my thing, which means that this thing diverges. And it diverges with comparison to this function. So that means that is answer choice B. So the last problem on this test is relatively a softball from the previous two. So they just want us to solve this integral. And as soon as I see a fraction that has a factor denominator, my mind instantly starts going to partial fraction decomposition. So let's just take that route. This is what we want to end up doing. So we want to get a over x plus b over x minus 2 equals 1 over x minus 2. We'll multiply both sides by this denominator, and that will get us a x minus 2 plus b x equals 1. I'm going to plug in x equals 2 to get that b equals 1/2. And I'll plug in x equals 0 to get that a equals 1/2 as well. That's negative 1/2, right? Because 0, so that's negative 2 times a equals 1. So that means that a is negative 1/2. Okay, so now my integral is, I'm going to bring a 1/2 out, and that's what I would be left with in my integral. So then it's just a 1/2 natural log of x minus 2 minus the natural log of x. But of course, right, that's not one of our answers. So we need to think back to our natural log properties. And we know if we have two natural logs being subtracted by one another, we just get the natural log of one divided by the other. And of course, we can't forget our plus c. That is answer choice C. So that's it for this video. I want to thank you guys for watching. If you enjoyed or found it insightful, give it a thumbs up or let me know in the comments. And let me know what types of things you would like to see. I'm probably going to keep doing these types of exam review things, but if there's any concepts that you don't understand that you'd like to see an explainer on, let me know. Thanks. Bye.